remote mode where the model is hosted on a remote service, and then the pipeline makes some sort of RPC call with your input data, and then as a response, the pipeline gets the predictions back. The other mode is where a model is pulled directly onto a worker that is running the pipeline, and then directly makes the inferences there. So I'll be talking about this particular local mode today. So in the past, before Beam released 2.40, developers had really two options to make inferences. Users of most machine learning frameworks had to write their own do-fun and code up all the logic to do the pre-processing, make the inferences, and then process the outputs. While this is pretty straightforward for prototypes, and that's the beauty of writing your own transforms in Beam, it becomes much more work if you're working with a lot of different models and different frameworks. The typical inference process has a lot of shared boilerplate stuff that is model agnostic, and you just would have to like repeat a lot of this stuff over and over again. So that's a major pain point. One exception to this is the TensorFlow RunInference transform. Like Harry mentioned earlier in our keynote, TensorFlow users can use a library that TFX has written within their TFX-BSL repository, and this contains a utility class to make inferences. However, with this route, there are some existing friction points. Firstly, it's not hosted in the Beam repo. Instead, it's under the TensorFlow/TFX-BSL repo, and therefore isn't as visible to Beam developers. Secondly, of course, this is exclusively geared towards TensorFlow, so it's not widely. So those who are using PyTorch or scikit-learn can't use this. It is this TensorFlow transform that has inspired us to make this general RunInference transform. So with the recent release of Beam 2.40, users can now use RunInference, a Beam transform, to make productionalized inferences in their pipelines. So what's so great about this? Well, first and foremost, it's RunInference has a clean and simple unified interface shared between all internal implementations, and takes care of a lot of boilerplate stuff that most models have to do. For example, on the left, we can see the usage of a shared class, which allows us to load the model only once per process and share it with all the do-fun instances created in that process. So this reduces the memory consumption and model loading time in your pipelines. We also implemented dynamic batching under the hood. To take advantage of the optimizations of vectorized inference that many models implement, we added the existing beam.batchElements transform as an intermediate step before calling the actual predict call for a particular model. This transform batches elements together, and then these batch elements are then applied with a transformation for the particular framework of RunInference that you are using. So for example, for numpy arrays, we call numpy.stack, and for torch tensor elements, we call torch.stack. Other features of this RunInference API include key forwarding, processing the output into a standard data class so that you can associate the output prediction to the original input example, and producing standard metrics that are relevant to typical ML pipelines, and then support for TPUs. So how can you, as a Beam developer, some frameworks. So we introduced RunInference implementations for PyTorch and scikit-learn frameworks in Beam 2.40. Like I mentioned earlier, TensorFlow users can technically do this already, but only through the TFX repo. So that's why there's an asterisk next to the TensorFlow logo there. We anticipate a consolidation into the Beam repo pretty soon. So how can you, as a Beam developer, use RunInference? Firstly, make sure you have version 2.40 or above. And you can simply add code that looks something like this. So from Apache beam.ml.inference.base, import RunInference. Notice that there's something called a model handler object inside of RunInference, and I'll cover that in the next slide. To import your models, you need to configure a model handler that will wrap around the underlying model that you have. Which model handler you use will depend on the framework and the type of data structure that contains your inputs. For example, if you're using a scikit-learn model and your input is a numpy array, just use sklearn model handler numpy. And for PyTorch tensors, use PyTorch model handler tensor. And we have a few others like support for pandas and then keyed tensor. Keyed tensor is just a dictionary that maps string to tensor. You will also need to specify inside of the model handlers a few parameters for just to help with instantiation of this model handler class. For example, the path to the pickled model for a scikit-learn model, or the path to the state dict, aka the model weights, for your PyTorch model. To the state dict, aka the model weights, for your PyTorch model. If a key is attached to the examples, you can simply wrap a keyed model handler around your base model handler object. As you can see here, we import keyed model handler and wrap it around the PyTorch model handler tensor. We import the keyed model handler from Apache beam.ml.inference.base and then wrap it around the PyTorch model handler tensor. So with this knowledge, you can start constructing more complicated pipelines, building up ensembles that utilize different patterns like the A-B pattern or the sequential pattern. So in your pipeline, you can create a branch by applying models to the same input P collection. This can be used for A-B testing. Here we have data read from some source. And then model handler A is passed to RunInference to create the variable model A predictions. And model handler B is passed to another RunInference transform to create model B predictions. You can also run models in sequence by chaining the RunInference calls in series. Here we can see that the data is read from a source, and then we use model handler A to make inferences, which creates the output called model A predictions. That is used as input and fed into RunInference that utilizes model handler B. So when you're doing a prediction with RunInference, the output P collection includes both the input examples as well as the inferences. So including both of these items allows you to associate the output, which input created the output. And if for some reason you need to use that information for any post-processing that you do. Here we have a do fund called post-processor that processes the output of RunInference. As you can see here, inside the process function, we unpack the tuple into a key and prediction result. Then to access the input, we just index using the example keyword, and then to access the predictions, we just index using inference. You can then do any post-processing logic that you have and then yield the result. And notice that we have this post-processor right after RunInference. Finally, inside RunInference, we keep track of certain types of metrics for monitoring purposes. Users can specify a namespace to which metrics for a particular transform can be associated. And we've included metrics such as the number of inferences and the count, min, max, mean of other information such as batch size, milliseconds per batch, information related to the actual inference call, such as latency, and other model loading metrics. If you run this in Dataflow, for example, on the right, you can see a mock-up of the UI for a job, and then the metrics will look something like this. So here are some of the features that we're looking forward to work on in the future. Right now, dynamic batching is done under the hood. And while you can certainly configure beam.batch elements to, for example, turn off batching by setting the max batch size to 1, and I'll show you that later in our demo. We want to see if we can provide an easier way for users to make batching optional. Users with a streaming pipeline may want to update their model weights every now and then, and we're looking to see if we can provide functionality via side inputs to allow these model updates in real time. And while you can certainly make API calls to other services now, we want to build better integration with remote services like Vertex API. In terms of other frameworks, we're currently working with NVIDIA to develop a TensorRT implementation of RunInference. Things look very promising, and we hope to have it ready soon. So don't know the exact version number of the release, but we're looking at maybe 2.42. But we'll see. So, and like I discussed earlier, we have support for PyTorch, scikit-learn, and TensorFlow. Other models that we have in mind are XGBoost, JAX, Statsmodels, etc. But I'd like to remind everyone that Beam is open source, and I just want to encourage everyone from the audience to contribute. If you want to work on one of these frameworks or have another one in mind, yeah, we've provided a base class in the GitHub repo, so feel free to implement on top of that. And then if you have any questions or ideas, feel free to make a PR or come talk to me afterwards in person. So I'd love to hear your ideas and see you guys contribute. And here are some related links, such as general how-to guide, documentation, and example pipelines using RunInference. And this is like on our Apache, like our main Apache Beam website, so you should be able to find it if you don't remember these links. I know they're kind of long. So that's the end of the talk. I will have a demo afterwards right now, so let's go to that. So this demo will require running a pipeline that takes in some input sentences. So I have 2 created here, but maybe I can add 1 or 2 more that the audience contribute. So if you guys can just shout out like 1 or 2 sentences that I can add to this list. Anyone from the audience. We'll see what the result is. So just any creative sentences that you want to see me add. Just shout it out. Like,
what's with the animals?
Okay. Probably double quotes. Okay. I guess we can work with that, and then we'll see the output of the pipeline. All right. I will also restart and run everything now, just because it takes some time to download the models and then run the pipeline. So. Cool. And I'll walk through the cells one by one, so don't worry. Okay, so in this demo, we will be using 2 models, the Tacotron 2 and the Wave RNR model, to synthesize high-quality speech from text. So this first model, the Tacotron 2 model, is a recurrent sequence-to-sequence model that generates a spectrogram from text. And then the second model generates audio waveforms from that spectrogram. Looks like I'll do this. I'll continue on, but yeah. There could be a connection issue or something of that nature, but I'll just continue on with this notebook demo, just so you guys can see see everything. Okay, well, I have a copy of this, and it's supposed to work, and it does, and this is what you're supposed to. This is what you're supposed to output. Well, okay, so the mic is plugged in, so I'll.
Beam Summit 2022. Keep Austin where?
Okay, so that's what you're supposed to hear. So